Hello, this is part 2 of the Basics of Magnetic Resonance Imaging, image contrast. One of the benefits of MRI is the amazing contrast between different tissue types and the ability to adjust that contrast by changing the way the data is acquired. For example, the images shown here show two different brain slices acquired at two different contrasts, one which we call T1 weighted and the other T2 weighted. Let us briefly explore what is meant by T1 and T2. So as I mentioned before, after sending in a radio wave, the magnetization is tipped into the transverse plane, where it then precesses or rotates about the magnetic field. As it is rotating around, the spins also realign themselves with the main magnetic field. And as a result, the net magnetization becomes realigned with the main magnetic field. The time constant at which this realignment or relaxation takes place is called T1, or the longitudinal relaxation time. Different tissues have different relaxation times. Now, in order to encode all of the spatial information in the image, we have to repeat this process many times, exciting the spins and then allowing them to relax for a brief period. If we wait only a short time before exciting the spins, as shown here, they will not have recovered their complete longitudinal magnetization, as shown here. As a result, we see more signal from spins that have recovered faster. That is, tissues with a shorter T1 will appear brighter. And that is what is shown here. The T1, or longitudinal relaxation time of white matter, is shorter than that of gray matter or cerebrospinal fluid, CSF, and thus it appears bright in the images. In contrast, CSF has a long T1, and thus areas with a lot of CSF appear dark in the image. Another important contrast in MRI is T2 contrast. Again, after sending in a radio wave, the magnetization is tipped into the transverse plane and it precesses or rotates around the direction of the main magnetic field. The frequency of this precession is directly proportional to the strength of the magnetic field. However, the structure of the tissue being imaged and the presence of other spins causes each spin to experience slightly different magnetic fields. Therefore, the spins don't all precess at exactly the same frequency, as illustrated here with magnetizations fanning out. The net sum of this magnetization is therefore smaller and decreases as the spins fan out or dephase. Different tissues have different rates of this signal decrease. Therefore, if we acquire an image at a specific time after sending in the radio wave, areas with a shorter T2 will have less signal. And that's what's shown here in a T2 weighted image. Brain areas with a short T2, such as white matter, appear dark in the image, while areas with a long T2, such as CSF, appear bright. So let me recap. In order to acquire an entire image, we have to acquire this signal multiple times, each a different phase encoding step. The first signal will have all the longitudinal magnetization available, but the subsequent echoes will have less signal if we don't wait long enough for this longitudinal magnetization to recover. The time between the RF pulses is called the repetition time, or TR. This longitudinal magnetization is then turned into transverse magnetization by the RF pulse. We then acquire this data a short time later. The time between the excitation, that is when we tip the magnetization into the transverse plane, and when we acquire the data is called the echo time, or TE. So the image contrast is determined largely by the TR and the TE. If we have a long TR, then tissues with a short and long T1 relaxation times will both have recovered, and we get very little T1 contrast. However, if the TR is shorter, then we get brighter signal from the tissues with a shorter T1 and darker signal with the ones with the longer T1, and we get good T1 contrast. For the echo time, if we acquire the data with a very short echo time, both signals and tissues with long and short T2s will have very similar signal. However, if we acquire the data with a longer TE, we get more T2 contrast. So in summary, if we acquire the data with a long TR and a short TE, we have very little T1 or T2 contrast, and so that's what we call a proton density weighted image. If we acquire the data with a short TR and a relatively short TE, we get a T1 weighted image. And if we acquire the data with a long TE and a long TR, we get an image that is primarily T2 weighted. Another important variable is the flip angle. In the previous examples, I was showing an RF pulse that tips the magnetization by 90 degrees, fully into the transverse plane. However, we can also tip the magnetization by a smaller or larger amount. how far we tip the magnetization is called the flip angle. It turns out there's an optimal flip angle that provides the maximum signal at steady state, which depends on the T1 and the TR. This is called the Ernst angle. And the cosine of this angle is equal to e to the minus TR over T1. Or in other words, the Ernst angle is the arc cosine of e to the minus TR over T1. So in summary, an MR image is formed by first putting the person into a strong magnet. This aligns the nuclei of atoms, in particular hydrogen bound in the form of water, with the magnetic field. We then send in a radio wave. This perturbs the alignment of the spins, and as they realign themselves with the main magnetic field, they send off a radio wave. And three, we apply magnetic field gradients to determine where these spins are located. The signal we measure then tells us about the amount of water in different parts of the image, in this case, the brain, and importantly, the magnetic environment that that water is in. These differences in the magnetic environment, which is determined by the tissue structure, and also such factors as blood flow and oxygenation, is what gives us the ability to see such striking detail and contrast, as well as the ability to see blood flow and oxygenation changes related to variations in brain activity, which we'll be exploring in one of the future lectures. Thank you.